And now part 4 of our video lecture on the respiratory system. So in the previous lecture we talked a little bit about in the previous lecture we talked a little bit about oxygen transport in the blood. Now we're going to look at carbon dioxide transport in the blood. We previously saw that there were two ways that oxygen transported in the blood. Oxygen could transport dissolved in the blood plasma at a very low percent, 1.5%. The majority of oxygen is transported in the blood in the hemoglobin of the red blood cell, 98.5%. Carbon dioxide is transported in three ways through the blood. It is dissolved within the blood plasma, that's the smallest amount, about 7%, still significantly higher than in the oxygen. It could also be carried as carbamino compounds. That means that it's combined with the amino acids in hemoglobin. So carbamino hemoglobin is hemoglobin with carbon dioxide transported on the heme portion of the hemoglobin. So it's not carried on the heme portion, it's carried on the globin portion. Let me repeat that because I think I got it wrong the first time. 23% of the carbon dioxide will be transported on the globin portion of the hemoglobin. In the oxygen is transported on the heme portion of the hemoglobin. Alright, and then the final way is as the bicarbonate ion. Now up at the top of this slide I've written out the chemical reaction. So we have carbon dioxide plus water will combine together to form carbonic acid. Now that's going to be catalyzed by an enzyme known as carbonic anhydrase. That's the last bullet point on this slide. Carbonic anhydrase will help form carbonic acid. Carbonic acid, it's an acid, and it will dissociate into hydrogen ions and the bicarbonate ion. So HCO3 is the bicarbonate ion. I don't have that written out for you, so let me include that. Bicarbonate. Now, this is a really important transport system because not only does it help transport carbon dioxide around in the blood, but it also serves as the primary pH buffering system for the blood. So the carbonic acid bicarbonate buffering system is the primary blood pH buffer. So we have our three different ways that carbon dioxide can be carried: dissolved, bound to the globin portion of the hemoglobin, and as the bicarbonate ion. Next, we're going to start looking at the actual movement of all of these molecules into and out of the oxygen. We're going to look at the movement of all of these molecules, carbon dioxide and oxygen, into and out of the red blood cell. Okay. But first I want to mention something called the chloride shift. I'm going to mention it now because I'm going to point it out in the next couple of slides. So I already mentioned this chemical reaction. So we had carbon dioxide binds with water to form H2CO3, and that's catalyzed by the enzyme carbonic anhydrase. Carbonic anhydrase, and that is a reversible reaction. Carbonic acid will dissociate in a reversible reaction into the hydrogen ion plus the bicarbonate ion. Now this does not actually occur out in the plasma. This occurs in the red blood cell because it's in the red blood cell where you have that enzyme carbonic anhydrase. So we have a little problem. We end up taking this bicarbonate ion, so we take the bicarbonate ion and we move it into and out of the red blood cell. But the red blood cell needs to remain electronically stable. That means if you move a negative charge out of the red blood cell, you've got to exchange it for a negatively charged ion. If you move a negatively charged ion into the red blood cell, you've got to move it out. So the red blood cell will pick up carbon dioxide, it will convert it into eventually the hydrogen ion and the bicarbonate ion, and that bicarbonate ion will diffuse out into the plasma, but you've got to balance that. And so this is something called the chloride shift. Chloride, Cl-, will move into the red blood cells in exchange for the bicarbonate ion. And also we will see the reverse as well. We eventually will need to take that bicarbonate back into the red blood cell, recombine it with hydrogen ions, reform carbonic acid, and then from that, using carbonic anhydrase, reform carbon dioxide and water. So when that happens, we've got to balance that against the movement of the chloride ion as well. So here is this movement. This, in case you, is external respiration. So we are inhaling oxygen. We're inhaling air, but it has a high partial pressure of oxygen. The oxygen, so here's the inhale, it will diffuse through the interstitial fluid, through the capillary cell wall, and into the plasma. Then that oxygen will diffuse into the red blood cell. In the red blood cell, the oxygen is going to combine with the hemoglobin. Hemoglobin, without oxygen on it, has a hydrogen. So it has this little hydrogen ion associated with it right there. Well, when the hemoglobin combines directly, with the oxygen, you end up displacing this hydrogen ion. That hydrogen ion at the lungs will recombine. Here's that recombination, and we're forming carbonic acid again. All right, where are we getting this bicarbonate? We're getting it from the bicarbonate that was traveling out in the plasma. So that's going to have to be balanced up here with that chloride ion. So anyway, we have our hydrogen ion, we have our hydrogen ion, we have our bicarbonate ion. We combine them back together to form the bicarbonate acid, to form carbonic acid. We break that apart using carbonic anhydrase, the enzyme, back into water, which a cell can always use, and carbon dioxide. So we start creating a locally high level of carbon dioxide, and that will begin to move out of the cell. Now, some of the carbon dioxide was transported directly associated with the hemoglobin, and some carbon dioxide, CO2, would have been simply dissolved in the blood plasma. So all three of those sources will come together. All three of those sources come together, and we move the carbon dioxide into the alveolus, and you exhale it. Now that was a lot to go through in one quick go, so you can back up and go through that again. But the beauty of this system, as I see it, is that a lot of times we think of one set of reactions or one set of events where you take in oxygen and you load it into the red blood cells and you deliver it to the tissues, and a completely different set of events where we offload the carbon dioxide. But in reality, take a look at this. This is one long chemical reaction with many that are hooked in together. So the act of taking in oxygen is linked with your ability to offload carbon dioxide at the lungs. And next we're going to look at this same set of reactions in internal respiration. So here we see in internal respiration what's going on at the tissue level. And guess what? It's almost exactly the same sets of reactions. Okay, so this time let's start with our carbon dioxide. So here's our carbon dioxide that's being produced by the tissue cells because it's going through aerobic cellular respiration, using up oxygen, producing carbon dioxide. So we have high carbon dioxide. It will diffuse out of the interstitial fluid and into the capillary, where it can be transported in one of three ways. Some of it will simply diffuse and go directly as carbon dioxide, 7% carbon dioxide in the blood plasma. Some of it will go in and it will attach directly to hemoglobin. And some of the carbon dioxide will move into the red blood cell. Then it will combine with the water, catalyzed by that enzyme, carbonic anhydrase, to form carbonic acid. Carbonic acid will dissociate into the bicarbonate ion and the hydrogen ion. So look and see what happens to this bicarbonate ion as it builds up. It begins to build up inside the cell, and it'll move back out of the cell and will be transported in the plasma as the bicarbonate ion. Look, let's go back to this hydrogen ion that was produced at the end, the hydrogen ion. The hydrogen ion is used to displace the oxygen from the hemoglobin. As it displaces the oxygen from the hemoglobin, you just have regular hemoglobin again. We bumped off, here we're bumping off this oxygen from the hemoglobin. That builds up, that locally builds up the level of oxygen, and the oxygen will diffuse out of the red blood cell through the plasma and into the interstitial fluid. Again, it's one long set of chemical reactions that allows you to take carbon dioxide from the tissues and deliver oxygen to the tissues. And it's the exact reverse of the set of chemical reactions we see in external respiration. Now, I know I'm a geek, but that's just cool. Alright, so just to see them side by side, I'm not going to go through this in any detail. You can see this exact same figure in your textbook. We see this relationship between the external respiration up at the top, that's at your lungs, and internal respiration between your tissues and the systemic capillaries down in the body. And we see that these are essentially the same sets of chemical reactions, all working in opposite directions, but it's one long chemical reaction. Alright, and then finally I want to end with a little note about smoking. You've heard me say a few things about smokers throughout this entire process. And the problem is that smoking is very damaging to lung tissue. There is no doubt that smoking damages lung tissue. And sometimes that damage to lung tissue might result in lung cancer. Now, people can develop lung cancer without smoking. All right. In fact, most lung cancers are found in people who don't smoke. But smoking will tremendously increase your chances of developing lung cancer, but it does other things as well. Smoke, the tobacco smoke, contains nicotine. If you remember back from our overview of the autonomic nervous system, there are what we call nicotinic receptors. Those are found in the terminal bronchioles, and they will constrict the bronchioles. So just by smoking, you increase your airway resistance. It makes it harder to move air into and out of the lungs. Another thing is smoking, the act of burning something, usually has incomplete or partial combustion. And from that, you're going to get carbon monoxide. Now, carbon monoxide is dangerous because it binds to hemoglobin even better than oxygen. So a person could die from suffocation, not being able to get enough oxygen, by inhaling carbon monoxide. And there will be a small amount found in cigarette smoke. There's also other just particulates, irritants, that will cause an increase in mucus secretion. And remember, all of that mucus that's below the level of the larynx is having to fight gravity to get back up and out of the lungs, get up to the larynx, be expelled, coughed up, and then swallowed down the esophagus. The movement of that mucus is helped out by cilia found in the trachea. Remember, the trachea is lined by ciliated pseudostratified columnar epithelia. The irritants will inhibit the movement of the cilia. So not only are you producing more mucus, but you are not moving that mucus effectively out of the lungs. It may begin to build up in the lung tissue, and that's going to reduce your ability to transport gases across the lungs. Over time, elastic fibers may start to be damaged, and that's going to cause a problem with lung compliance. You're not going to be able to expand the lungs and then have elastic recoil of the lungs. That leads to a form of chronic obstructive pulmonary disease, so a form of COPDs, known as emphysema, which is trapping of air in the alveoli, so you can't exchange it with fresh air, and this is going to reduce the gas exchange. So this is what a smoker could look forward to, maybe not in the next 5 years, but probably in the next 10 to 15 years if they continue to smoke. In fact, when we look at the averages for a person who smokes, so down at the bottom, right down at the bottom here, we have the age in years. All right, and along the side, so that's on the x-axis is age in years, and along the y-axis we have respiratory performance. So it's looking at your top value about age 25, and then what happens over time. The top blue line is what you can expect in an individual who never smokes. You will see a decline in performance as you get older. That's just one of those facts of aging. You see a decline in performance. But compare that to the red line, someone who is a regular smoker. You see a much sharper decline in respiratory performance on average in a smoker. Right? If we go down to about age 45, we see the first dotted line. An individual who stops at age 45 will immediately see a decrease in that reduction. All right, so it'll be a lot more like the slope of the line we see in an individual who never smoked. Keep on smoking past age 45. Just keep on smoking till you're about 65. Well, here's the problem. You'll notice a little line there between the green area and the purple area. That's a line associated with disability. That's if your respiratory performance gets low enough that you're not able to adequately deliver oxygen to your tissues. At that point, you're going to have to exist on supplemental oxygen. All right? Now you'll notice that the sooner you quit smoking, the less likely it is you will ever get to that point. All right? And these are just averages. So the sooner you stop smoking, the less likely you are to get to that point. Now this person over here who stopped at age 45, by the time they get to that area, maybe they're around 80 years old. Okay? Human lifespan is getting, on average, up into 78 to 80 years old. That's on average. All right? So there's a good chance that if you make it to that time, if you smoked until you were 45, right there, you're going to enter into disability, compared to if you never smoked. If we continue that line out a little bit longer, you're still not having to exist on supplemental oxygen. If you wait even longer until you stop smoking, you can see that at this point you're going to be on supplemental oxygen. This point, of course, is the point you don't want to get to. That's the point where you will die because of your inability to take on enough oxygen. Right? Now, I know everybody has their Uncle Joe who smoked until he was 98 years old and died of a car wreck while he was drinking. All right? But that's a very unusual person. These are the averages. This is what an average person could expect. You're probably not going to be that person who has really strong lungs and could smoke until you're 100 and something years old. And then on average, half of you will probably have an even stronger response to smoking than these averages. So the take-home message is, if you are smoking now, stop as soon as you possibly can. It is one of the most addictive drugs there is, but do everything you can to stop smoking as soon as you possibly can, because you're at least going to reduce the number of years where you may be dependent on supplemental oxygen and fighting for breath. All right, and on that happy note, we're going to end the video lecture on the respiratory system. Hopefully you will have listened to this before December, before we get back to classes next week after Thanksgiving. So have a great Thanksgiving, and I'll see you guys in about a week.